Welcome to this lecture in the ongoing series of lectures on real analysis. Today we'll be starting a new module. This will be about differentiation. This and the next module will be about differentiation. This is a very interesting concept and is the starting point of so much of mathematics. And we'll be only able to look at a very particular case of that mathematics, but that is all that we can see in the course of in any course of real analysis. All right. So let me not recall anything in detail. What we have done basically so far is, discuss the notion of continuity and a related notion of limits. And now we'll do differentiability. All right, so let me start with definitions that we need. And this will be a lot of definitions, this whole lecture, but very important ones. So, okay, so let X be a point in R. Right neighborhood of X is any set of the form U intersection X comma infinite, where U is a neighborhood of X. So pictorially, if you have X and this is your real line, this is X, then right neighborhood is first you choose a neighborhood, it could be anything, and then you just intersect with this whole thing. So this part becomes your right neighborhood. A very simple definition. And similarly, one can define left neighborhood, which I leave you to define. One can define that. And now finally let me define left and right boundary point. So let I be an interval and A be the infimum of I and B equals supremum of I. So then if A and B, if A is a real number and A and I, then we call A the left boundary point of I, and if B in R and B in I, then ... So then we call B the right boundary point. So let me just remark as to what we are trying to capture. So suppose we have an interval of this sort, meaning some interval of the sort a comma b. Then we'd like to call this the left boundary point and this the right boundary point. So basically this definition takes care of that. And if you had an interval of this sort, let's say like this. So this has no boundary points. This guy has no left boundary point, but it has a right boundary point and so on. So basically this definition is a complicated way of capturing of something very, very visual. So very simple definitions. And another set of very simple definitions are in order. Okay, so this time let X not be a real number. We define the open right half plane corresponding to X naught as the set h x naught plus. So this is a notation, and it is defined as those points in the plane where x is greater than x naught. Okay, so let me just draw a picture. Here we have the plane, and let's say this is x naught, or maybe let me draw it somewhere here. This is x naught. Then the open right half plane can be depicted as follows. So the orange, or rather whatever is this color, that part is the open right half plane. So every point which has x coordinate greater than x naught, all of those points are here, and precisely those points are here. Okay, and this is the notation. Sorry, so let me change the highlighter. Yeah, open right half plane. Similarly, one can define open left half plane. H x naught minus, and that is something that you can do. Okay, and now we want to define rays. So we study rays in plane geometry, Euclidean geometry, where a ray is like a half line. So it starts at a point, but it proceeds only in one direction. So that's a ray. We will be interested in rays that are not vertical. So if we have, this is my xy plane, then except for these kinds of rays which go in either in the vertical upwards direction or vertically downwards direction, except for these two rays, we'll be interested in the other kinds of rays. So so we make the definitions with that in mind. So let x naught comma y naught be arbitrary. And what we want to do is the following. Let me draw a picture. So let's say this is x naught comma y naught. And we want to define a right ray. So we define a right ray starting at x naught comma y naught is, so what is it? Let me first intuitively say what it is. So it is any ray of this form, except for the vertical rays. It is any ray which proceeds, whose x coordinates increases. So this kind of ray is not a right ray, but this kind of ray is a right ray. So a right ray starting at x naught comma y naught has the point x naught comma y naught, and all its other points are in the right half plane. So let me just say formally what it is. So starting at x naught comma y naught is any set of the form is any subset of R2 of the form x comma y. Okay, so this is basically x comma mx minus x naught plus y naught, all the points where x is greater than equal to x naught. So since we've studied the equation of a line in high school, you see where this is coming from. So if you substitute x equals x naught in this coordinate pair, and which you are allowed to substitute, then you get precisely x naught comma y naught. So this particular point is here in this set. So this particular point is here, and if you have x greater than x naught, then you see you just follow this line where the slope is m. So this tan theta, meaning if this is theta, then tan theta is m. So for some real number m, if m is positive, then you go like this. If m is negative, you go like that, and if m is 0, then you go like that. So that's a right ray. and let me just draw it maybe for peace of my mind. So any such thing is a right ray. Okay. And similarly, one can define left rays starting at a given point. Okay, so that you can do. Again, these definitions are also very, very simple. Now for a little bit more complicated of a definition, we'll define cones. So let this be a point in R2 and fix a right ray, and R, or let me say rho, equals x comma m x minus x naught plus y naught x greater than equal to x naught be a right ray. So we have fixed it. Starting at x naught comma y naught. So now what I want to do, I want to define a cone centered, or not really centered, but a cone which has to do with that ray. So let me first draw a picture. So this is x naught comma y naught, and let's say this is a right ray. Okay, so what I want to do is I want to define a set which is of this sort. It's like a cone. So it's a union of so many, all of these kinds of rays. So whatever is the slope of this ray, which is m, I want to take all the rays which have slope more than m minus epsilon and less than m plus epsilon. So I want to take all those rays and take their union, and that will be a cone, which will be like, in some sense centered at this rate. I'll say more about this centering business. So here is the thing. So let epsilon greater than 0. The epsilon cone about rho is defined as the set C epsilon rho as this. So we take x comma theta x minus x naught plus y naught all those points in R2 with the property that x is at least x naught and theta is allowed to deviate from m by less than epsilon. So this is exactly what I said in words. If you fix a theta with this property, then you vary x with this property, then you're generating a ray of that slope. Theta is the slope, not the angle. So I've written theta. Theta is usually used to denote angles, but here I'm using that to denote slope. So please don't get confused. So let me draw a picture. So this region is the C epsilon rho. So it contains this point also. C epsilon is this cone also contains this point x naught comma y naught. But as I have defined it, it does not contain these rays. So this ray has slope. This dotted thing has slope m minus epsilon, and this dotted thing has slope m plus epsilon. So I am not including those two things in this definition, although I could. Doesn't really make a difference, but I didn't. Okay. And what about the centering business? The thing is that this angle and that angle are not equal the way I've defined it. This angle is not equal to that angle unless m is 0. If m were 0, then this would be a horizontal line, and then indeed these two angles would be equal, but this is deliberate. The way I've defined it is deliberately so that these, I want the slopes to be plus and minus epsilon away from the slope of this. And we'll see why that is. Technically speaking, it wouldn't make a difference if I had defined it as a symmetric cone, but I didn't because this is more convenient for my purpose. Okay, so these are epsilon cones, or this. Okay, so this is not the epsilon cone. This is the epsilon cone. Yeah, fine. This is fine. This is the epsilon cone about a given ray. So you can similarly define epsilon cones about left rays. There's no, you can easily manage that. Okay. Finally, we'll define tangents. Tangent to a graph. And let me give a preamble as to that this is not really so easy to define. And why are we doing all this cones and rays business? So we have an intuitive notion of what is a tangent, but it is not so easy to define. So suppose I have this curve, the parabola, which we see in high school physics a lot. Yeah. And intuitively, if I have some point on this, so intuitively, the tangent at this point is this pink line. So one would like to say, okay, a tangent is a line, tangent to this curve is a line which intersects the graph at exactly one point. But this definition is clearly not a correct one because then, this line would also become a tangent line because this also intersects the graph at exactly one point, this point. So clearly just intersecting is not enough. And then what do you do? How do you define tangents? Maybe one would like to say that it is a line which touches the curve at exactly one point. But then what does one mean by touches? Touches is not a mathematically precise word. So we need to define what is a tangent properly. Okay, so this is what I'm going to do. So let f be a function defined on an interval I. So I is an interval. We are not talking about functions which are defined on arbitrary domains now. Okay, and this I is non-degenerate, so this has positive length. What do I mean by that? It means that if you take the endpoints of I, then the difference of those two endpoints is positive. So I is of the form a comma b, or of this form, or of whatever a comma b, this form. Then the length is basically b minus a. That's what I mean by length. So this b minus a should be positive. It shouldn't be just one point, the interval. Okay, so of positive length. And now let a in I be such that there is epsilon greater than 0, or let me not use epsilon, let me use some other symbol, maybe alpha greater than 0, such that a comma a plus epsilon is contained in I. So all what I'm trying to say is that a is not a right boundary point. A is not the right boundary point of I. That's all this is saying. Okay. So now we can define a tangent. So with that, a right ray starting at a comma f of a is called a right tangent to gamma f. Gamma f is the graph of f, remember. Let me write down what that means. It means x comma fx, x in the domain, is a right tangent to gamma f if something happens, if something which may look somewhat complicated, but we have to do it. If for all epsilon greater than 0, there is delta greater than 0 such that the epsilon cone about right ray rho, so let me call this rho, right ray rho starting at a comma fa, so such that the epsilon cone about the right ray rho contains gamma restricted to, or rather gamma of f restricted to a comma a plus delta. Looks complicated, but let's see what am I trying to say. Let me highlight. We are trying to define a right tangent. Okay, so let's say this is my point a comma f of a, and I have some right ray starting at this point, and I haven't drawn the graph of the function. We'll get to that. And now what is this saying? He's saying, suppose you fix an epsilon greater than 0 and you take this epsilon cone. So let's make that epsilon cone. Something. And let me also shade it, because I've been shading it all the while. So this part. So once you fix an epsilon greater than 0 and draw this epsilon cone about this given ray, then we are saying that there is some delta greater than 0. It may be very small, but it is positive, such that the graph of the function restricted to this right neighborhood of a is contained in this guy. So the graph is contained for some delta. So this is a, this is a plus delta. And what we've stipulated is that there is some delta greater than 0 such that the graph of the function above this interval is contained in the epsilon cone. So the more stringent you take the epsilon, meaning the smaller you take the epsilon, the delta you may need to choose smaller and smaller delta, but it will still remain for that region, for that amount of time within the chosen epsilon cone. So you see, this is kind of trapping the function to be close to this tangent line if you come close to the point A. So this should feel like a correct definition of the tangent, is what I'm trying to say. This is much like our epsilon delta definition of continuity. There what we demanded was that the function be trapped in a band. We say the function is continuous at A. If for all epsilon greater than 0, you draw this epsilon band, And then we demanded that there is a delta greater than 0 such that whenever you make this interval of, when you make this interval of length delta and consider the graph of the function above this delta, then the graph of the function is contained in this epsilon band, provided delta is small enough. So this is much like the definition of continuity. We have just changed the shape which contains the graph of the function. That's all. So the two definitions, the definition of continuity or right continuity and right derivative, or not derivative, the definition of right continuity of a function and the definition of the right tangent, they are very, very related, except that we've changed the shape that was involved. In the definition of right continuity, this kind of shape was involved, a right band, and here we have a right kind of cone. So that's the only difference. Okay. So similarly, one can define a left tangent. So left tangent is something that I leave to you. So we have defined right tangent finally. Okay. And here is a lemma. Let me add a page. Here is the lemma. Let f I to r be a function defined on an interval I. Let a be not, let a in I be not the right boundary point of I. Okay. Now what is the theorem? It says that if there is a right tangent, if there is a right tangent to the graph of f, at the point x, a comma f of a, then it is unique. So note that here we have the indefinite article a right tangent. We are not saying the right tangent. We cannot say the right tangent unless we prove that it is unique. The definition a priori does not guarantee uniqueness. Okay. So so just like if you have a limit of the function existing at a point, then it is unique. Similarly, the right tangent is also sort of a limit. Rather than limit of a function, it is sort of limit of some kind of lines attached to a function. Whatever, ignore that comment if you don't understand. I did not make any precise comment anyway. So I hope you understand and appreciate the importance of this. And let me not write down this proof, but convince you that this is actually true. And I will do that via pictures. You can easily convert this into a formal proof. So you have this point a comma f of a. And for the sake of a contradiction, assume you have two different candidates for a right tangent. Suppose this is a right tangent and this is also a right tangent. Let me use some other color, maybe green. So we have two different candidates for right tangent. All right, so if we choose epsilon small enough, so this could have slope m, this could have slope m prime. So so just make sure that this m denotes the slope. I'm not writing that m is the slope, but please take note that this is the slope. So just choose epsilon small enough so that the epsilon cones about these rays are disjoint. So sorry, this is, yeah. So choose epsilon small enough so that the epsilon cones are disjoint. Oops. In YouTube, forward button is your friend. This is the epsilon cone about this ray. And this is the epsilon cone about the other ray. Okay. This is C epsilon rho prime. This is C epsilon rho. This white line is rho. This green line is rho prime. So we can always choose epsilon small enough so that this epsilon cone is these two epsilon cones are disjoint, simply because you can choose epsilon to be, less than m minus m prime by 3, let's say. Just choose epsilon equals to that and you'll be fine. So now if these both are indeed right tangents, then there exists delta greater than 0 such that graph of f restricted to a comma a plus delta is contained in the epsilon cone about rho, and there exists delta prime greater than 0 such that the graph of f restricted to a comma a plus delta prime is contained in C epsilon rho prime. Let me make this green. Right? So the white one is coming from, this is coming from the fact that this is the right tangent, and this is coming from the fact that this is the right tangent. Fine, but then if you take, so let delta naught equals a minimum of the two deltas, then the first one says that graph of f restricted to a comma a plus delta naught is contained in C epsilon rho, and the second one says that the graph of f restricted to a comma a plus delta naught is contained in C epsilon rho prime. But these two things are disjoint. Or rather, well, I shouldn't say disjoint, they meet at only one point. This is the only point in common. All the while I was saying that these two things are disjoint, but please note that it was a misstep, a very minor one, because this point is in both of them, but no other point is there. Okay, fine. So these two, this and that is contained in that. So so this implies a contradiction. Because if you take the point, let's say, just choose any point here which is greater than a. Just choose a point B which is greater than a. Then b comma f of b is here as well as here. But b comma f of b is different from a comma f of a. A comma f of a is the only point common to both cones. And b comma f of b, it says, is here as well as here, as well as here, and that's not possible. Okay, so this is a very simple proof, and this is more or less rigorous. I said that I won't be writing details, but this is a rigorous proof, in fact. You can easily just write few more lines to make it purely formal and not refer to the pictures at all, but one should understand only in terms of pictures, or as much as possible in terms of pictures. Not only in terms of pictures, sorry, as much as possible in terms of pictures. All right. So here, what do we want to do? We want to look at some examples, and let me show you some examples where right tangents exist. So our first example is where you have f from R to R, x going to x square. This is our function. And I want to show that the right tangent at x naught comma f of x naught, which is 0 comma 0. So I'm taking x naught equals 0, exists. So this is our claim, and I mean, in fact, we claim that the right tangent is the horizontal line. So let rho equals x comma 0, x greater than equal to 0. So this is the horizontal line. We want to show this is the right tangent, and this should be clear from the definition. So whenever you draw an epsilon cone, some part of the function will remain in the epsilon cone for some time. If you choose a smaller cone, then you have a smaller epsilon. Smaller delta. So C epsilon rho is what? C epsilon rho is all the points x comma theta x where this is less than epsilon. Because m equals 0, right? M equals 0 and y0 is also equal to 0 if you correlate with the notations we had earlier. So just make sure that you follow that this is the epsilon cone about this horizontal ray, right? Yeah, so where I also need to say that x is greater than equal to x, no? Greater than equal to 0, yeah. We have the, yeah. Okay. So I want to show that there is a delta. I want to show that there exists delta greater than 0 such that the graph of the function above a comma a plus delta is contained in this. That is what we want to show. But I think just if you take delta equals epsilon, then you're fine. So if you take delta equals epsilon, let delta equals epsilon, then for x in this, meaning this, we have x comma f of x equals x comma x square, which is so we want to show that this is in, we want to show that this point is here. So this is equal to x comma x times x. But mod x is less than epsilon. In fact, mod x is less than delta, which is equal to epsilon. Right? So this is indeed of that form. Just think of this as theta, and this satisfies this constraint. Why is mod x less than delta? Because x is here. I mean, epsilon equals delta. So I don't know how else to say that. Epsilon equals delta. That's how we chose it. So that's the thing. Maybe this is very confusing the way I have presented it, but you can take this as an exercise if this is not clear. Okay. Similarly, I want to show that the right tangent here exists at the origin. And this I will leave as an exercise. Basically show that the right tangent to the absolute value function, this is the absolute value function graph, x going to mod x, and the right tangent at the origin is just this line. And that's because if you choose an epsilon cone, then in fact delta, you can take whatever delta you want. If you take delta equals 10,000, that's also fine, because from 0 to 10,000, the graph of the function is contained in this epsilon cone. So arbitrarily large delta works. All right. So make sure that you get this one, even though I did not explain it very well, somewhat unneatly. But it's very simple. You just make an epsilon cone and just note that delta equals epsilon itself works. Okay. Is there anything else? Maybe I want to show an example where the right tangent does not exist. Let's see, do I have it? Okay, maybe I'll do non-examples next time. For now, this is enough. Already this is a fairly long lecture. So as usual, like, comment, share, subscribe. I also have Patreon. The link is in the description below. Thank you for listening, and I'll see you next time.